Hello, we've got a situation. I've got 3 students and they need a place to study.
For this project, we created an environmental sensor which records light and temperature using Adafruit Data Logger Shield in Arduino. We then created a case for our sensor to ensure protection against the environment. Then we collected data from 5 different common study locations around the UT campus and used that data to model which location would be most ideal for studying based on temperature and light levels. First, we designed the light and temperature sensor circuits on Tinkercad. Then, we implemented a circuit we designed onto a breadboard. Creating the circuits on these 2 mediums made it easy to correct any mistakes and allowed us to easily manipulate our sensor. Once the circuit design was finalized, we soldered the Adafruit data logger onto the Arduino, following the design we previously made. To create the sensor case, we brainstormed a design on paper, then implemented that design onto a CAD software, Fusion 360. The design was finalized, printed, and evaluated and ensured to fit our sensor well. The sensor was then used to collect data. With this data, we were able to do linear regressions to see the relationship between light and time and temperature and time. We did the linear regressions by hand calculation and by using the data analysis function on Excel. We also modeled this onto a paper model, identified the stocks and flows of a light temperature model, then modeled onto any logic, and determined various parameters that affected the light levels and temperature.
During the design process of the sensor case, we took many factors into consideration, including ventilation, locations of the ports and SD card reader, and the location of the temperature and light sensors. Based on this, the design of the sensor case incorporated slits throughout both pieces of the case to ensure that there's sufficient airflow while the sensor was operating. The top piece includes a square opening that allows temperature and light value data to be collected without being hindered. Furthermore, the edges of the case were smoothed out to prevent any issues while handling the Arduino. When we printed the design of the case, there were notable qualities that differed from what was intended. First, it was evident that many of the splits on the vertical walls of the case didn't print properly, which can be attributed to the 3D printer's addition of supports during the printing process. Given the size of the supports, it was difficult to remove them, and it was decided that they would just be kept in place to prevent any damage to the sensor case. The case still provides adequate ventilation through these inhibited slits, but the primary ventilation depends on the slits and opening on the top piece. Another issue included slight errors in measurement that resulted in the ports not being aligned with the openings in the case, but they are still accessible. Similarly, errors in measurements resulted in the height of the case to be greater than that of the sensor, resulting in the SD card being inaccessible, but this was easily corrected by elevating the sensor and placing a folded sheet of paper underneath. As far as the fit of the sensor within the case, the sensor is provided with sufficient room so that it can be removed in place without any difficulty. The thickness of the case was made so that not only would the sensor be protected, but that it wouldn't be too bulky to move around.
We started our paper model with 2 nodes to represent the sensors in our Arduino, light and temperature. First, we looked at the type of light. We have sunlight, a geographical interdependence, which increases the light in a room and provides heat to increase the temperature in a room given the correct building materials. Then we have LED light, a physical interdependency, considering that unnatural lighting is part of the room's infrastructure, which we are assuming has no effect on temperature and only increases the light in a room. The next parameter we considered was the presence of glass or windows. This is a physical interdependency because it has to do with the building materials of the room. Glass increases the light in a room by letting in any from the outside and increases the temperature in a room because it's an insulator. The next parameter we considered was the flooring and walls, which is also a physical interdependency for the same reason. Carpet and drywall both increase the temperature in a room because they are insulators and trap heat, while tile, assuming the presence of AC in the room is also decreasing the temperature, holds this cooler temperature better than the other materials and causes the room temperature to stay low. The next parameter we considered was the room size, which is also a physical interdependency and increases the temperature of the room as the room gets smaller, allowing less ventilation, making the link a negative relationship. Finally, we considered the number of students in a room, which we originally thought was a logical interdependency based on the decision of a student to choose the room, but then when considering that the number of students is linked to temperature, realizing that it's actually a physical interdependency because it's based on the amount of human capital in the room. We chose these parameters because we believe that they are the most impactful to our sensors based on the data we want to collect, and because they are the criteria you can check off when walking into a study area by simply looking around and finding the perfect spot.
In order to test the relationships from our paper model, we collected data at 5 different locations around the UT campus. We picked a study room in the EER atrium, an ECJ classroom, the Union Building, and the FAC. These locations are all very different common environments for studying, which is why we chose them. We collected the data all in the same day, and since we only had one sensor, the time of day at which data was collected at each location was different. This, among with other variables such as number of people entering the room, amount of natural light, etc., are very hard to keep constant between the different locations we chose. Since these conditions were very different for each of the locations, it was easy to pinpoint a correlation between the variables in the data collected.
After collecting the data, we computed simple linear regressions by hand and by using the data analysis function in Excel. We can see how accurate our data is by looking at the R-squared value, which tells us how close our actual data fits our model. We considered an R-squared of 0.6 and above to be accurate, which was the case for the light value in the FAC, the light value in the ECJ classroom, and the light value in the EER study room, as well as the temperature in the ECJ classroom and the temperature in the EER study room. The rest of the data has a poor R-squared, meaning that the data does not fit the regression line well and will not be accurately represented in our later AnyLogic model. From the residual plots, we assumed the EER atrium and ECJ classroom data to be linear, and we assumed the EER study room, union, and FAC data to be nonlinear, meaning we cannot use the typical y equals mx plus b slope, and it is not likely modeled correctly with the approach we used later in AnyLogic. Based on our parameters, the type of light is the same in the atrium and the FAC because they are both lit with natural light. However, the EER data was recorded at night and the FAC was recorded when it was cloudy, explaining the trends in the data. Similarly, the Union, ECJ classroom, and EER study room are all lit with LED light, so the light value should be constant and high. However, our data does not reflect this. This is because the sensor receives a higher influx of light when it is first turned on, and then the amount of light levels out over time. Based on the presence of glass and windows, the same results can account for the light value data, and similarly in the FAC and atrium. The temperature should be lower than the other locations because the absence of sunlight by recording at night and during cloudy weather, which our data proved since these locations were about 8 to 15 degrees lower than the other locations. Based on the room materials, the carpeted areas of the Union, FAC, and EER study room should have higher temperatures than the tiled atrium and ECJ classroom. This is true for some, but not all of our data, because while the temperature is higher in the Union, it is not higher in the FAC and the EER study room, so it can be assumed that there are other more effective parameters at play. Based on the number of people in the room considered alongside the size of the room, the EER study room should be the warmest location, which is shown by our data. However, the temperature eventually cools as we assume the automated AC adjusts for the high density in the room.
From our data, we modeled the cause and effect relationship between time and light and time and temperature in each of the locations we chose. We modeled these relationships in AnyLogic using the equations we determined earlier from the linear regression analyses. The value of the stocks were the intercepts, while the value of the flows were the slopes. Our model is somewhat accurate for the locations that we determined as having linear relationships with time, but not accurate for the nonlinear ones. Even for the rooms that had linear relationships based on the data, we cannot conclude that the model is necessarily accurate since our simulation model doesn't include parameters affecting the temperature and light in the rooms, like flooring type, presence of windows and glass, number of people in the room at any given time, type of light, and more, since these are hard to quantify and model in a relationship.
Based on our data, we would say the EER atrium is the best location if a student values temperature since the recorded temperature in the atrium is around the ideal studying temperature of 25 degrees Celsius. The Union would be the better location if a student studies better with high levels of light. However, if a student studies at the EER atrium during the day while the sun is out, the atrium would be ideal for both conditions. From this system, we learned that there are many interdependent factors that affect our system's light and temperature values. Fluctuations in natural sunlight in areas that have a lot of exterior-facing windows, the number of students present in the space, and the type of light present are among the conditions that can affect our measured parameters. In general, we learned that systems are a complicated network of nodes, all of which have multiple interdependencies, making it hard to find specific relationships between causations and correlations. One of the main challenges we faced in this project was sensor accuracy. Since we chose to purchase sensors that were inexpensive, the inaccuracy of the data can be attributed to the poor quality of the instruments used. We addressed the issue with the temperature sensors by checking the thermometers in the rooms we were in and adjusting the measured temperature values to the standards set by the thermometer. We found this to be effective, making it easier to compare the data recorded between the different locations. Another main challenge was the SD card not properly collecting data from the Arduino board. We fixed this issue by collecting data directly into the computer instead. This is not ideal since it made the sensor dependent on the computer and made it a lot less portable. Our favorite part of the activity was building the sensor and sensor case in the Texas Invention Works facility. For the most part, this is our first time building a mini computer to collect data, so we enjoyed seeing our engineered design put to use for a common purpose that all students, including us, face. Our least favorite part of the activity, however, was doing the linear regressions by hand. Our favorite part of the course is developing a new perspective of how to view the world around us. A decision as simple as finding a good place to study can be broken down and measured by numerous parameters. In this case, light and temperature were the two parameters of interest, but many other, more difficult parameters to measure, including the construction materials that make up the room, how crowded the space becomes, and the dimension of a room could also be incorporated into the decision. The concepts and skills developed in this course has far-reaching effects on how we approach problems in the future as professional engineers.